virtual camera. Turn on the camera. Wave at people. Maybe I get to wave. Why is that not sharing the camera? Oh, because it thinks it's the broadcast camera and the OBS camera. That's the OBS camera. There we go. Good evening, everyone. That's because it hides my microphone because it thinks my microphone is background. Sweet. Okay, so that gap there now is microphone gap. Nice. Can't even see my Rode microphone. Okay, guys. Now this is we've got none on the YouTube. Hopefully I'm streaming to the right place because I haven't changed it since last time. So I believe it in the right place. You guys can all hear me properly? Yep, thumbs up. Excellent.
Good morning.
Good morning.
How are you doing?
I'm pretty good. It's just yes. So this is the you guys had summertime kick in, so you've got the daylight savings have just come on
no.
for you guys, and
That's bad for you, isn't it?
So now this is 10 p.m. at night,
Oh my God.
and so it will be midnight before you guys actually let me go. So we could have a discussion potentially of moving this an hour earlier, so it starts at 9 for you guys rather than at 10. But then, some of you don't want to wake up until like 9:55, or some of you even maybe the alarm set at 10 past 10 in the morning, roll over, prop up your phone in the bed and start watching on the stream. But yeah. So now I've finished my lecturing in New Zealand now, so this is my only lecturing, and I just have marking of the games that my students have been making here to go through. So it's a fair bit easier to do this now. So I just have to recognise that I'll be up a little bit later on Tuesday nights. But that's all good. Okay, so we're 13 past. Okay, so we've got a few of you here already, and we expect the others to start turning up, and I've got at least one currently viewing on YouTube, which suggests that I have put it in the right place. Bit rate seems to be fine. I would like seeing we had a look at a couple of games last week. I would like to spend some time doing code reviews with you guys, right? Coming up. Now, for this lecture, I've still got I've put in a debugging lecture. I don't know how much explicit debugging you guys have been taught. You're taught sort of software engineering-y kind of techniques, but how much debugging explicitly have you been through? You can write it, or you can say hello and say it. Just check the chat. So very little. Cecilia's done very little. Figuring out debugging on your own is just cruel, right? Because debugging's like, so when you think of code development, right, and they talk about the standard code lifecycle, and you say you spend like 10% of your time like creating the code, 90% of your time, 10% making, like 20%, so twice as much debugging, and then the other 70% is in maintenance once it's actually working, right? So you actually spend the vast majority of your time maintaining code you've written, but you usually spend like twice as much time debugging as you spend creating code. Oh, and that's a quote I've left out of my slides, which I will have to ask you. So I've uploaded the slides to the GitLab again, and used the Claude Sonnet 3.5 new, because they've just released the new version, to turn these slides into the Markdown. So if you, yes, so so yes, printing variable manually is still the most common way of doing debugging, but yeah, so we're 16, so we'll get underway now. So got a warning on my studio. What is the warning on the studio? Oh, it's just saying that I'm lower than recommended. So it's saying I'm a wee bit blurry. That's right. I'll close that down. Okay, so I'll switch over to being in the bottom corner. And we're going to talk about debugging today. Now, one of the things that I advise people about coding and debugging, and I'm going to start with this, is you guys are currently learning to code, right? And debugging is harder than writing code, right? Because to write code, you have to think, what do you want to achieve? And then you try and write that out in lines of code. So you're trying to turn something you understand into something you don't understand perfectly, but you're learning. Okay, so in your stage of development. Debugging is taking something that you don't quite understand and trying to fix it, right? Because you don't understand what's wrong with it and you don't understand how it's supposed to work. And so debugging is harder than programming. And in fact, I would argue that for normal production code, you have to code at about between 50 and 70% of your actual coding capability, right? You have to code dumb, right? You have to use systems that are more obvious than you're capable of using. You have to use techniques that are simpler than you're capable of understanding, so that when they break, you can use your more advanced knowledge to fix the simpler things, right? Because debugging is harder than programming. So in fact, you should put a lot of your effort into extending your ability to debug and extending your programming ability, but then code at less than that ability. Right? So it's kind of an interesting, when you're doing exploratory programming, you don't debug, you just explore, you try things, you do random stuff, you see how things work, you pull them apart, you intentionally break them to find out how they work. Okay, so that's exploratory coding, where you're coding to learn rather than coding to produce. In game development, those happen in two basically different phases. There is a code to explore phase where you're just exploring capabilities of the game engine and you're exploring like new techniques yourself, and this is an exploratory phase. And then when you're trying to actually make your game to go in production, you don't experiment with the cutting edge of your knowledge. That is where you experiment in a game jam with your current edge of your knowledge, and then you pull back from that into the game you actually want to make, and then you can make it and debug the game, right? Because you're exploratory coding, you don't need to debug because it's going to have bugs, it's going to be awful because you're exploring at the edge of capability. But if you want to release something, you've got to have fewer bugs, and therefore you cannot code at the edge of your capability, right? So you have to kind of have these two mindsets. Am I exploring, or am I doing production code, which I will debug, right? And so that's what we're talking about today. Okay, so old school. So they're like the really old school is you make sure your code works before you send it to the compiler, because and this may seem insane, but I Oh, and I should actually turn on. Do I have the front side of that? No. Do I have the front side of that? No. Neither of the. Oh well, I'll try and get out of the way. So when I started university, and still, this is now 30 years ago, 32 years ago, we actually still had a mainframe, and we still had CPU cost on the mainframe, which meant when we compiled, we used up some of our money, right? Because it's a bit like with the AI chatbots now, where if you use the APIs, you pay per token. So we had CPU cycles, and we were paying per CPU cycle. So the technique was to manually debug your code before you sent it compile, because you didn't want to use up all of your CPU budget. That's super old school. Nobody does that shit anymore, right? We actually use the compiler as part of our programming process. It is integrated into the way we program, it's integrated into the way that we think about writing code, is that we have IntelliSense on our IDEs. We have, sometimes if you're using interpreted language, you have real-time compiling of the language happening all the time, or interpretation of the language happening all the time. So bugs are immediately seen because they are processed and evaluated. And in the old school, you tried to only write code that worked, and therefore bug fixing was something's broken. So as I said, there's this exploratory coding where you can use the compiler to find errors and give hints, and but there are still some issues with not knowing what is possible. So you're still exploring the language and exploring the engine, right? So debugging comes from this kind of a combination of exploring and fixing bugs. Okay, and if I go up, there we go. Okay, so one thing we do is actually debugging is hard, and so we try and prevent bugs from happening in the first place. Right? Now this seems a stupid thing to talk about in a debugging lecture, but if you can stop bugs from happening, you're usually better off. So one of the things we know that is often sometimes I call them big sausage finger errors, right? Is you're typing stuff and you get something wrong, or you think something's named something and you make a spelling mistake, and you call it print instead of display or something, right? So this often happens when there's a spelling error or a word error and you've not been consistent, right? So one of the things we do is using a naming convention so that you try and make sure you're using the words in the way that you mean to. Understand what you are trying to achieve. One of the hardest bugs to find are bugs that are from your own ambiguity about what you're trying to do. If you don't understand what you're trying to do, and you're just sort of pushing the compiler, you're pushing the code to do stuff that you don't really understand, then those are the hardest bugs, right? Because you don't understand what you don't understand, and so you don't know why it's not doing what you don't know what it should do anyway. And so the best option there is actually spend a little bit more time sort of thinking through what it is you're actually trying to achieve, and what would be the logical, explainable steps to achieve what you're trying to do. Often you can talk out what you're trying to achieve in your code, and that'll help you understand, giving a different perspective of the intent of the code, right? And so one way to minimize the bugs you have is to think about your code and think through what you're trying to achieve. Using variables correctly and keeping code modular. Spaghetti code, the more code you have to hold in your head when you're writing code, the more likely you are to create bugs because of the dependencies that you've forgotten about, right? So one of the things we talk about is if you have, and I should have an example of this later, if you have two lines of code that always appear, a create and initialize, right? So let's say you're doing an object-oriented thing and you're creating an object, and you have a line that's create object, and then you have a line that initializes the object with the values in it, right? And those two lines are always together, right? If you miss one out, then you get a bug, and it's kind of, well, why should you have to write both of those lines all the time? How about you just wrap them into a single constructor that does creation and initialization together? So you now only have a one line of code that does all of that, right? And this isn't to speed up your code. It's not to say, calling functions are faster, and it's not because you're going to necessarily, save much time by typing out this much longer function than if you just typed out this to individuals. It's because it prevents bugs, right? It prevents errors of you only calling one and not the other. So there's this whole idea of if you can change the way you code, you might be able to decrease the number of bugs. Outside of the game code itself, one of the things that also, before you start editing your game code and before you start playing around with code you've been writing or code other people have been writing, or starting to find where a bug is, you check that you're in the right repository and that you've updated the repository, you've got the latest version, you're in the right branch. Check stuff that isn't the code. Check you are in the right file, in the right repository, right? That you don't happen to have two files that have similar names but are editing different parts of the file. So one of the common things I see people do is they'll be trying to fix a problem, and they'll make a small fix, and they'll compile and run, and nothing will happen. So they'll make another small fix, compile and run, nothing will happen. They'll make another small fix, compile and run, nothing will happen. Make another small fix, compile and run, nothing happens. And then they realize they haven't saved. So they'll then save the file, compile and run, and everything has changed. And it's kind of, which of those four things changed that output? And it's kind of because you didn't save between those changes, and so you didn't actually recompile with the latest version. So that sort of make sure you've saved your changes, and make sure that you are actually doing a fresh compile with the content you have in engines. Certainly in Unreal and Unity, there are bugs that are created by the engine getting a bit tired, had too many things happen. So in Unreal, sometimes you just close the editor down, restart Unreal, and it fixes the problems you had. Right? So the bug was nothing to do with your code, it was to do with the editor you're using. Godot and Unity are a little bit better, but sometimes it can be useful just to refresh the system, so that before you start screwing around with the code, you actually make sure the system around the outside of the game code itself is working properly. Okay, so one of the things that we also do when we're debugging, and this is something I was trying to work out how I would set an exam on, because I've sort of having like whole courses just on debugging and professional programming. In fact, we had a professional programming course that I used to teach at Yervik, which was 50% code reviews and 50% just talking about writing good code. One of the keys of someone like me doing debugging, if I'm working in a language I know, and increasingly that's not true because I have to work across many languages, but I would look at a block of code and immediately my brain would filter it for risk, right? I'd go through and say, what are the riskier lines of code that might happen in this file, right? And so that orders where I go looking for a bug, right? Which is one of the reasons why when I'm coding and if I'm looking at other students' code in C++, the more code I've seen, the more errors I've seen, the better I've got at connecting a risk factor to lines of code, right? So if you use a particular type of line of code, I will scan over and go, oh, that's a risky line of code. I know that line of code causes bugs for some people, so let's go and look at that one to see if there's anything wrong with it. Right? So I don't know that there's something wrong with the line of code, but I know there could be. So for example, one of the ones we just, using the standard, if a equals 5, right? So using an equivalence in an if statement in C, one of the standard problems was if you miss out one of the equals, right? You miss out one of these two, you end up with A is assigned the value 5, and that will return the value 5 because an assignment returns its value, and 5 is true because 5 is not 0, and so that will return true and assign A to the value 5. If you miss out the second equal here and just have A equals 5. So for some people, the answer was you have a linter, so you have a pre-process that looks over your code looking for inaccurate loops, not compile errors, but just non-standard use that we have in our company. We call this linting, so it's searching for the fluff, searching for the wrong, for the things where you're out of line. And so some people have a linting style where they say if nominal is equivalent to variable, right? Because if the static value is equivalent to the variable value, then I can, if I miss out one of these two equals, if I only have like that one, right? My compiler will throw a hissy fit and go, no, that's, you can't assign A to 5, 5 can't change, right? And we'll say, oh, that's a left-hand error. So I force the compiler to check for me the bug that could happen. But as an experienced programmer, we would generally look at, pointers are always a problem and can cause errors. Copying objects and not knowing, did you do a deep copy or a shallow copy, therefore are the memories overlapping or not? So these are like, when I copy and change, does that change the value in both places? Do you know the ownership of your variables? Do you know the ownership of your objects? Iterating through things, hitting the ends of things, missing by one and running over the end of an array, starting from 1 instead of 0 in an array. So just lots of things that when we see, because we've seen people have errors in that lines of code like that, they feel like they might have errors. Now that's something that you get from experience. We don't expect you to have all of that experience yet. So unfortunately, although this is the way that experienced programmers actually do debugging, it's something you gain from experience in the language that you're trying to debug. It's not something you can just read in a textbook and borrow from other people, right? It's something you develop yourself from your experience. Okay, so these are kind of ways of thinking about bugs, and so I have this idea of risky code. But what is a bug? Well, so a program is supposed to do X, but is doing Y. So I wanted you, when I gave you, I gave you X as an input, and I wanted you to produce, so in this case, I gave you W as an input, and I wanted you to produce X, but in fact, you produced Y. That would be there's a mismatch between what I wanted you to do and what you're actually doing. Okay. So to know if there's a mismatch between these two, you have to have an objective X and a current state Y and know that they're not the same, right? You have to know that it's not actually doing what you wanted it to do. And this leads us to this idea of test-driven development, where when you're using your code, and a simple bug might be I press space and it doesn't jump, right? So you go, aha. So you had a desire that it moves up, and a behavior it's not moving. Okay, good. Okay, that's a bug. We had an input space, and we knew that was supposed to create one output. It didn't create that output. Now for test-driven development, we create a lot of tests where we give it an input Y and an output. We have create input-output pairs, and a bug is now a form of a failing test, right? So if there's a bug, what you do, so in sort of test-driven development, there's two types. You can either do test-driven development where you program all the tests up and then write code to satisfy them, or you can kind of do a mixed version where if there's a bug, you create a test, right? So the idea is as soon as you're trying to do something, you go, oh, the code doesn't do what I expected it to do. You go, I must expect something to happen here. I will write a test so that A, I know that I've fixed this bug, and B, if it comes back, I will detect that, right? Because I know now that this is the kind of thing that might go wrong in my program, right? Because one of the problems with test-driven development, if you adopt it wholeheartedly and start with test-driven development, is you start writing tests for the code, and those tests can never actually happen. They never actually fail. They're never a situation where your code might produce this kind of error. And so you put a huge amount of effort into developing tests which are never at risk, right? You're never actually at risk from having this input not match its output. And it's only really when you get to writing code and seeing where it breaks that you kind of know what tests you would need. So that's why test-driven development hasn't like taken over the industry, is because unfortunately you have to write far too many tests because you don't know where your program might fail. So one approach is this sort of, if there's a bug, you write a test to fix it, and you use regression tests to ensure that your bug doesn't return. All right, so for example, if like one of the very old techniques is putting print statements in. One way you do that is you put your print statements in, but instead of just putting a print statement in, you put in an if debug, then a print statement, and then you can remove, so you can turn off debugging, but you leave the print statement there because you want that print statement in there if a bug occurs in the future. So you don't just put it in and then delete it and then come back later and put it back in and then delete it and then come back later and put it back in and delete it. You leave it in a hash if-def kind of function where you compile it in whether you're doing debugging or not when you're not doing debugging, and it leaves it in there and does that kind of role for printing thing out, right? So this is where we talk about using add debugging in hash defines. So and this could be a statement or a if-def, which is the hash defines. For some systems they'll have a debugging, so Unreal has a debugging tool. You can also use debugging logging, and so in debugging logging you say, well, I'm going to log this but only when it's a bug, right? But for test-driven development, it's a reasonable way to start with some bits where you know what you're trying to achieve, but then you don't try and write exhaustive tests because you can't really. But when you do get a bug, that's when you can write a test. The big challenge in games is that they're often state dependent, and bugs usually, the sort of test-driven development has to be state independent, so that you can run unit tests and you can rerun tests and you can run regression tests. For games, often our debugging regression testing has to be replaying the game to get to that point and then seeing if the bug still happens. Right? And to do that, your test case has to be storing all of the user input and the random number generated. If you're starting with any random stuff, you've got to be able to recreate exact functionality. And if you use any sort of system random variable, and you seed it with time of day or something, you're not going to be able to perfectly repeat that sequence of play. And so for perfect regression testing, is actually quite difficult in games. Not impossible. And some games, once they have their debugging system put in, they use that as their game replay system. All right, so some of you will have seen kill cams where they replay the bit of the game before you died. Actually, really useful as a debugging tool, because if you've got a sequence of actions that led up to a crash, you can watch what the player was doing just before the system crashed. Right, and so that's a debugging tool. And then you go, oh, people really like to see what was happening just before they died, so let's use that as a replay tool. Right, so you build a replay tool for your debugging, and then you get to use it as a feature in your game. So hypothesis-driven debugging. So this is that kind of scientific approach to debugging. So some of you, when your code isn't doing what you intend it to do, right? There's a couple of things people do, right? So the unfortunately naive and early learning phase, which actually most of you are still in the early learning phase, so it's not too bad, is you just keep whacking in print statements and watching the print statements, and as I think we said before, toggle breakpoints that will then break the code at a certain point, and then you can use your step through F10 to step lines and F11 to step in, and so you step through your code watching your variables, trying to work out what is going on, right? Because you just don't know what's going on, and so you're actively exploring your code. Right? Now, that's okay if you've got a very small block of code and you've got a very tight position where you know the bug is happening. As code gets larger and more complex, you don't get to do that, right? That's only doable when you've got a small number of files and a small amount of code, and it's very hard to get you to write code that is large enough when you're at uni, so that you actually can't use your standard whack and print statements and just find it. An improved technique is this hypothesis testing approach, where you go through the asking good questions of your code. Right? So the test-driven stuff, you write a test, doesn't tell you anything about how to fix it, just tells you, have you fixed it? Right? It doesn't tell you how to fix it. With a hypothesis testing is you think, okay, I'm trying to work out what my code is doing, and so I'm going to make a hypothesis that if I change this part of the code, it is more likely to do what I intended it to do. Right? So you're not just kind of randomly Rubik's cubing it. Well, Rubik's Cube, you can do it systematically, but so you're not just kind of randomly whacking moles. You're thinking, okay, can I make a change that would narrow down what is causing this problem? And having thought about what might be causing the problem, what might be wrong, can I do something to fix it? Right? So what is the fix for the bug? Right? What is that hypothesis that I'm making? Now, one of the nice things about thinking about it as a hypothesis, you're saying, well, if I do, like, I'm going to do this and see if it fixes it. If you can remember those, one of the nice things is you can start sort of trying to work out how to write good hypotheses and how to understand your code better. One of the ways of kind of working out and making those hypotheses is sometimes called rubber ducking. You guys have all heard of rubber ducking, where you explain your code to a rubber duck. I sometimes explain my code to my cat. And by explaining the problem out loud, the force of having to turn your often multi kind of prong in working in parallel, lots of different parts of the code all fitting, the force of having to squeeze that into a linear narrative and try and explain it to something forces you to grab all that mush and drive it it's like taking a big bowl of meat and turning it into a sausage, right? The the force of having to do that and having to squeeze it into a linear form makes you think differently about what your code is doing. And in that change of perspective, that can help you fix an understanding issue you were having. And once you fix the understanding issue, then you fix the bug, right? That's how that works, is that useful realignment. Now, in fact, this rubber ducking technique, to some extent, it's what English teachers think happens when you write an essay, right? Now, I personally don't find this because I'm slightly dyslexic, and I've always found linear prose writing difficult and annoying and of very little benefit to me. Right? So I don't think in English prose. Right? So I don't think how other people do when they write essays. And when I write essays, it doesn't help me think about the problems differently. Writing code helps me think about the problems differently, but writing text doesn't. However, there are a bunch of people, potentially more neurotypical people than I am, who benefit, again, from this forcing it into a linear narrative, forces you to address your thinking and forces you to think about what you are doing. And that's why they say writing an essay helps you think, because for them, their ideas are all mushy and all over the place, and it's only in writing sentences that do their mushy ideas get formed into something that actually is meaningful. Right? Now, for coding, when I write code, I am turning something into something meaningful, and I can test it, which is better than you can do with language. But I find talking about things helps me think through them, and writing code helps me think through them. I don't find writing in English helps me work through ideas, but some people do. So it may be that when you want to understand the problem, maybe for you, writing an essay about what you're trying to do in your code will help you think about it. That's not my experience, but it might be yours. So I'm not going to dismiss that. But most programmers tend to use the rubber ducky approach of talking it through rather than writing it all down, because the linear talking is what changes the perspective. Okay, so now we get to our favorite approach. Common debugging approach is to use print string. However, as I said, you don't just do straight print string. What you do is you leave it in. If you're doing something in C-style language, then you can often have an fdef debug, and then you define debug. And what debug does here is I have some sort of formatting, and I will I'll have the input come in and with extra variables, and then I'll print to standard error, the formatting, and all the arguments. Else, so if dev debug do this, else define debug as doing nothing, right? And then so this is the idea that here I can include debug statements all through my code now, and if I turn on debugging, all of them are an fprint to standard error. And if I turn off debugging, then all of them return void and disappear. Right? So it's kind of, I can turn on and off debugging. And one of the standard approaches is that you then do that with levels, right? And you do, debug level 1, debug level 2, debug level 3. And if you set different debug levels, if the debug level is above a certain level, then you print, right? And so you have some that are on debug level 1, so debug level is nobody prints. Debug level 1, the most important things print. Debug level 2, the next level of important things print. So the first level and the second level. And level 3, the first, second, and third level. and level 4, the first, second, third, and fourth level. And so as you set debug level 4, you get everything, and you kind of scroll up and down your debugging levels. Now, again, I'm also printing this to standard error rather than printing it out to console. That means you can actually separate debug messages from your standard console messaging. It also allows you to save all those debug messages to file. If you are wanting to redirect standard error into file, you can cache them and create a log. Because one of the things you'll notice, I'm sure you've had Windows crash, and you've probably had Linux, a program doesn't work on Linux or something, and they like Windows, you can go and check the log and see what was happening. Right? That is debugging, right? They're just doing a log, not to track you. That's not why they've made the log. They've made the log because they need to debug. And what they found is that, I'm going to put a whole bunch of this information into the log so that when a bug happens, I can go and find it. Because if you've got a bug that crashes your program, one of the problems... Now, this is slightly less than it used to be, but when we were coding... and in C, you still have this problem. A print statement requires flushing, right? So what could happen is you could have print statements and you would cache the print statement, and then the program would crash before it had flushed the print buffer. And so your program was actually getting further than your last print statement because your print statement wasn't blocking and didn't stop there. Your print statement was asynchronous, so it could keep doing these operations, hit a crash point here, and then die, taking the print statement with it. And so you spend all this time above that print statement trying to fix the code above it when actually it's happening after that, right? And that's true for logging information. It's true for a whole bunch of things that are asynchronous. And so there are actually interesting challenges when you're running with this, with using I/O as part of your debugging, where you might not be able to trust the last print statement. So you can certainly go to the last print statement that actually worked. You're probably after that, but you don't know if it happened before or after this print statement. It's probably close to where that print statement is. All right, so you have to kind of think more and be more cautious when you're using prints as part of your debugging. One of the things that's becoming more common in programming is something that was happening 20 years ago when I was coding as a student, 30 years as a student, was you create your own consoles and your own windows that are your debugging interface to your program, right? So one of the things that you can do is relatively easily, and actually in all the game engines very easy to set these up, is you set up a console. So when you hit enter, when you're still creating your code, right? So that's Unreal. When you're creating your code, you actually think, okay, I know that I'm going to have to test lots of things and change lots of values and test lots of values. And so what I'm going to do is I'm going to create a little module that when I press enter, it pops up a console, and then I can type things into that console and they will affect variables in the game. Right? So you hit enter and you go set lives equals 10, and then that goes in and you take that string and you have a wee processing function that goes, if string equals set, then parse the next string to say, oh, that's the word lives. I've got a variable called lives. Great. That's connected. And then equals 10. I go, okay, so I'm going to make lives equal the value coming in from the console. Right? Some of you, hopefully, have found that games sometimes accidentally leave in their consoles, and you can go in and cheat by finding the debug console and editing the code, right? Or editing values, right? So some games accidentally leave them in or have turned them off, and then someone hacks the game in a a regx, so you change the executable, and you go in there, you change the bit, turns off the debug console, you turn it back on. Suddenly you've got debug console access, and you can do anything you like in the game. So sometimes leaving it in this problem, but the idea is you can create GUI interfaces or command line into like a console interface to the game, and so you can manually debug it while it's running. So IM GUI, so immediate mode, that's what the IM is for, is a tool that is for C++ code. It generates a vertex buffer, which you can then print and you can display on screen with your OpenGL at any moment. But it creates a GUI interface that is able to edit GUIs and connect up to parts of the program that you're working in. And you can just, anywhere in your program, you can type, to attach a window to objects in the system. And the idea of that is I can very easily, therefore, interact with my code and interact with the variables in the code from my pop-up GUI window. And that certainly makes it easier for some of your designers to find bugs and find code and help. So in Unreal specifically, so if any of you are doing Unreal stuff, you'll find that you have this development only flag, which you can use as your debugging, and you can kind of set up print string in developer only so that when you have something happen, you can print out, so print to log, or you can print different strings to screen, to log, change text color, change the duration it's up, and for deployment only, which means when you compile and run for release, none of these get shown. Right, so this is when you're in developer mode, basically you had all your debugging information available, and it won't end up in your release mode. Right, so that's sort of the automating of that if debug technique. In Godot, one of the techniques for debugging is to add tools in your Godot editor. Now, the Godot editor is a Godot game, interestingly, right? So it's written in, I think it's written in C#. But it's a Godot game running. The editor is running on the Godot engine as Godot game. One of the things you can do is in your GD scripts, you can have an at tool at the top, and I'll have to check that 4.3 has the exact syntax, but you can go and look at it. When you do that, it means the code in that script will run in the editor, and so you can actually write additional bits of code for some of your objects to highlight, to add arcs to show their jumping range, to have them, some of them you can tell them to fall in the editor so you can see what happens, so you can kind of have parts of the game run while you're in the editor to show off what's going on, because you can create tools by saying this is a tool block, right? And that can help you with your debugging, because you're able to write tools that help you get more information about what your code is doing. And you can use step-through debuggers to help you understand. So one, you're displaying things, as well as getting this idea of step-through debugging, which you get from the editor. There's also a visual logger, which is a really neat way to understand what's happening in code like Unreal. And there are debugging tools that you can add for almost all systems. Game engines all have some form of debugging tool built in. And so, yeah, to activate the loggers, you can see you can do visual loggers. So, yeah, the console kind of, if you're in the visual logger view, put it open. So here you can add, and it highlights things, it adds additional information. And it's a great way to kind of see what's happening by logging events, and you can sort of get lists of who's making actions and a timing for when things are happening, so you can trace through and visually see what's going on, right? So this is a neat way of adding. You can add the visual logger, and so you can enable it, and then trace what's going on. Now, to some extent, the immediate mode GUI is doing a bit of this visual logger, and there's a good YouTube talk there for it. If you're in Unreal, so Unreal itself has a powerful console in the background. So you actually go tilde, so the home thing, to open up the console, and then in your Unreal game, you can, in your debug, when you're playing from the editor, you can actually get a whole bunch of stats about the game that's running while you're running it from the console, right? So you actually ask about stats and you get information, and you can find out a whole bunch of stuff about what's happening from inspecting those stats, right? So you get the memory stuff, you get what's happening in the engine, you can get stats about what functions the game's calling. So there's lots of those additional console commands if you're in Unreal. And again, I think Godot, there's a tool that's just been added to Godot as well for this kind of console level debugging. The last thing, or couple of things to go, is when you're debugging. I know it's faster just to put in print statements, but often it's better to put those into a log and save your debugging information into a log system, because if you can therefore control the level of your logging, you can either log a lot or log nothing. If you're trying to release the game, maybe you only log the core things, but when you're debugging, having those extra logs can really help you understand. And if you can use log view tools where you can find when this occurs just using Control F, but you can also look for like recurring things, and you can look at the shape of what's happening and when it's happening. If you save your game logs into your game folder, it means that if you give your code to someone else and they have a crash, you can then get them to forward the local logs, and then you can look and go, I can see where you crashed, right? And so generally what I do is, when I'm logging, you log the start of the program, and you log any parameters that come in, or any parameters that you've set. You also will log the version of your game that is being tested, because one of the things you'll find is that as you start getting further along, you'll have branching, you'll have different executables, you won't necessarily be logging your versions accurately, which you should do. You should log them accurately. But then you'll send something out to be tested. It'll get a crash, someone will report something, and if you don't know what version of the code that bug is in, then you start fixing it in something where it's already been fixed and it's the wrong version, and it's just right? And so you spend a huge amount of effort trying to fix something that isn't a problem anymore. And so it's really important in your log files to print out versions of the tool. Now, one way to do that is you you include into the logging information something from the repo, where you actually go, okay, can I grab the latest build from the repo that I'm in, and then put it into a text file which I can grab and include in my log to say, well, this was the version of the software that created this log, right? So there's various ways to kind of think, how do I attach a version number to my log, and then my log is more meaningful, right? And therefore my tests are more meaningful, and I can debug my code more efficiently because I know I'm actually debugging the code that I intended to debug. It also allows you to log things and find because when your game is still working, finding a bug when you've got an output, it's just not quite the one you want, is much easier than the game froze, everything stopped working, and it's kind of shit, I can't get information, I can't test things, I can't try different things because it's just crashing. So logging is really useful when you are in that situation. And this gets us to what we call telemetry, where you start looking at how you log enough information about your game to identify crashes. Sometimes you'll log locally, which is like what Windows does. Sometimes you'll log to a server. One of the other reasons we use logging to servers is that it also gives us an idea of how people are using the game, what parts of the game people are playing, because if you log when people enter particular parts of the game, you get that back and you then can build a map of how much players are using different parts of your game, and therefore how much you might need to create more content in an area. You can see that they're just turned off and they find an area boring, there isn't a good hook for it, so you can start thinking about how you update the game to respond to the way that people are playing it. And so these logs don't become just about crashing and just about bugs, they become about understanding how your game is being played. Because at some higher level you might think, well, I want my game to be enjoyable, and so if my game's not enjoyable, maybe that's a bug. Right? It's something your game's not achieving that you want it to achieve, right? So we can use the term bug in various different ways. All of these tools have step-through debuggers. I hope you've all used step-through debuggers and set up step-through debuggers. Blueprints have step-through debuggers. You can toggle breakpoints on blueprints. You can set breakpoints in Godot. And one of the nice things about setting breakpoints is that in the editors is you can go and expect and not just print out a single value, but inspect all of the values and watch all of them change and see what was going across the whole stack rather than just the one that you were thinking of, right? So it might take a little bit more than adding a print statement, but it certainly gives you more and much more information. In games, often what we'll do is we will change what the viewport does, right? And what is rendered. Because so sometimes if you do lighting only, you can see the world differently, and so you render it differently so you can see what's going on. Sometimes you'll render wireframes, sometimes you do lighting only, sometimes you'll do text only. So you render it in various different ways to try and inspect and see the world in a different way. And automated testing, right? So for dev builds, using things like GitLab continuous integration and GitHub Actions, and third-party tools like Jenkins, these are all tools. So GitLab continuous integration means that it will try and integrate your code and run tests against it and see if it is still working. And one of the neat things is, and actually, so if you're going to set up GitLab continuous integration for Unity projects, can be a wee bit harder because you have to actually spin up Unity to check often to see if the game's working. And so what we do is you usually create a Docker container that spins up the game and runs the game. If you're not building it for an executable, you need to spin it up in the Unity editor and play it in the Unity editor and then run through a sequence of recorded inputs that you then play back through the game to make sure that it still gets to the same point or it still completes. It is work, but if you get a really, really big game, and certainly none of the games you make this trimester are big enough to really need that level of spin up a Docker container, install Unity on the Docker container, run your code through, play it in Unity so you can see that it is running against the regression test and integrates properly and all the code works. You're not big enough to do that, but in a professional team you would be, and so that's when you'd start trying to do that. And you can do the same sort of thing with GitHub, where you can trigger automatic testing, you can trigger automatic integration, you can test for bugs, and that's the idea of being able to find bugs if you can find them before the game stops. So if you can create a whole bunch of tests and find bugs, or some people call them monkey testing, where you just hammer it with inputs and see if it breaks at any point. That idea of stability testing and just random input testing can find errors that you can then fix, because if you release code and suddenly you have hundreds of people using it, that's when you'll find things that you didn't test properly and you didn't think about, and then you'll find these bugs, and then you have to fix them on a live system, and that's always annoying, right? So that's where this kind of automated testing can really help you. And that's where you do the setup automatic builds and tests. Takes time to set up, but it saves time in crunch and it saves time at release, right? So, and it makes it easier to find those errors. Okay, so that was my 50 minutes of talking about bugs and debugging. Do you have any questions about debugging? Aha, there is a question. Okay, so should you have a constructor and a separate init function? The constructor sets up the member variables, the init sets up the parts of the system, or should you can be combined? I talked to ChatGPT about this last night, and it suggested keeping the two separate. What do you do, Simon and classmates? Think. Okay, so the reason why ChatGPT would suggest keeping the two separate, given I told you, if you always call them together, make them a single thing, is because if you're doing memory management, you may want to have a factory class where you don't actually do memory IO, so you don't actually create a new. What you do is you say, right, get me a version of this. Now, the idea of using memory management and you being in control of memory management would mean that you would want to keep these two separate, right? So you have one where you construct, and then you have another where you set all the values correctly, because they often are worried that if you just have a single function, which is a construct and initialize, it means you're not in control of your memory, right? Because like when you pair in construction and destruction, it's this init constructing thing. Like, it does that always create new memory? Does it not always create new memory? You might not know that it's creating new memory because you're just initializing it, and it just secretly creates memory in the background, and then you have this huge memory leak. So there are people who would certainly argue, no, you always separate construction and initialization, because construction is a massive hit on your memory, whereas initialization is just assignments, and that's always fine. So they are, no, definitely keep it separate, so you know that it's separate. The other approach is, oh, no, I have a factory that deals with that, and therefore I don't have an initializer and a constructor, or I don't have a constructor and then an initializer. I just call my factory. My factory handles that, and that's all done in the background, and it handles all the construction and all the deletion of memory. It handles all the memory management, and everything is just a single call to, get enemy. And with, create enemy, and you give it the values to initialize with. And the other factory will handle all of the memory associated with that. I don't ever have to. And I just, I create and release, and it deals with new and delete. Right? So it depends on how you're managing code. Memory management was a massive problem over the last, 40 years of using C++ and using unmanaged memories, and having Java having to do garbage collection and stuff because people weren't good at managing memory. So it really depends on how you're using code and what you're trying to prevent. So that's what I think. I see Kai's typing, so he has a different opinion to me. It's interesting. So sometimes if you're trying to prevent a certain type of bug, right, where say, you try and initialize something and it hasn't been created yet. So there are times when you might want to do that kind of singleton thing of saying, well, if it doesn't exist, create it. But then you create memory holes. So it's kind of the best way of doing it. Hopefully Kai will finish typing shortly. So yeah, I'm I'm willing to defend either decision, Cicely. But in graphics in C++, I would have a stack allocation. I would have stack allocate a cube class. The cube deals with its own memory management. So when I declare it, it keeps calling its constructor and creates buffers on the GPU, vertex, and elements buffers. So if I can call an init function separately, I can manage its memory. Yep. So Kai is again, that's in the constructor versus the initializer. I, as programmer, want to be in charge of how the memory is managed, so I will have a constructor. That is very different to initializer because once I've constructed it, if I want to reinitialize, I don't want to have to call another constructor. I just want to reinitialize it to its new use case. I don't want to create a new one. Right? So that's why you might keep those separate and say, well, actually, they don't always run together. I don't always construct something every time I initialize things. I actually will reinitialize something back. Having constructed it once, I'll reuse it many times. Okay, so yeah. But that's, yeah, again, it's how you manage memory and how optimal you want to be and who you want to be in charge of that memory. So different programs use different systems. Okay, any other questions? Because I'll take a break now, and when I come back, I will go into checking on the groups to see how you guys are all going, and get a catch up with everyone. Okay. Any other general debugging questions? Okay. Right. Well, I'll see you in 10 minutes. So, because I have to go and take the tablet off my son and make him sleep. And I'll be back at 1:30, and but I'll be back and I'll come into the individual groups. Okay, so bye bye people online, and I'll see you in the individual groups on Discord.